This is the entire CompTIA Network Plus, all 5 domains condensed into one sitting. No filler, no 8-hour lecture, just every testable fact and every exam trap the night before you walk in. The exam is 90 questions in 90 minutes, and you need 720 out of 900 to pass. 5 domains, weighted unevenly. Domain 5, Troubleshooting, is the heaviest at 24%. Domain 4, Security, the lightest at 14%. All 5 add up to 100% of your score, and we cover every one. One habit decides pass or fail. Do not just listen. When you are unsure, pause and say the answer out loud before I do. Active recall is why people pass. Passive listening is why people pay the $390 retake. 5 domains, 1 sitting. Domain 1 starts now. Domain 1 is 23% of your exam. That is almost a quarter of your total score. If you underestimate this domain, you can drop a letter grade on your total before you have even touched a troubleshooting question. We are not going to let that happen. The OSI model has 7 layers. You need to know them cold, forwards and backwards. From layer 1 to layer 7, physical, data link, network, transport, session, presentation, application. The mnemonic from the bottom up is please do not throw sausage pizza away. Top down, all people seem to need data processing. Burn one of those into your head before you walk in. The exam doesn't just want the layer names, it wants devices and protocols mapped to specific layers. At layer 1, physical, you're dealing with cables, hubs, and repeaters, anything that moves raw bits. At layer 2, data link, you have switches and MAC addresses. This is where frames live, not packets. At layer 3, network, you have routers and IP addresses. This is where packets live. Layer 4, transport, is where TCP, that's Transmission Control Protocol, and UDP, User Datagram Protocol, operate. Port numbers live here too. Protocols map to layers as well. HTTP, FTP, DNS, and SMTP live at layer 7, application. SSL and TLS live at layer 6, presentation. NetBIOS lives at layer 5, session. TCP and UDP live at layer 4, transport. IP, ICMP, and routing protocols live at layer 3, network. MAC addresses and frame switching live at layer 2, data link. Physical cables and raw signaling live at layer 1, physical. Here is a trap the exam loves. They will ask at which layer does a switch operate. The answer is layer 2, but then they add the phrase layer 3 switch in the question stem. A layer 3 switch adds routing capability, so it can operate at both layer 2 and layer 3. Read the question carefully and look for that qualifier. Network appliances each have a specific function, and the exam will describe a business need and ask which device to deploy. A firewall filters traffic based on rules. A stateful firewall tracks connection state and knows whether traffic is part of an established session. A stateless firewall only checks individual packet headers with no memory of prior packets. An IDS, that's an intrusion detection system, monitors traffic and generates alerts. It does not block anything. An IPS, intrusion prevention system, monitors traffic and actively blocks threats in line. The single most tested difference, IDS is passive, IPS is active and inline. A proxy server sits between internal clients and the internet. It can cache content to improve performance, filter requests to block certain sites, and hide internal IP addresses from external servers. A reverse proxy sits in front of your servers and protects them from being directly exposed to the internet. A load balancer distributes incoming traffic across multiple servers to prevent any one server from being overwhelmed. It also provides redundancy. If one server goes down, the load balancer routes traffic to the remaining healthy servers.
A VPN concentrator manages large volumes of simultaneous VPN connections. You would deploy one at a corporate headquarters to handle hundreds of remote workers connecting at the same time.
Here is the IDS versus IPS trap. If the question says the security team wants to monitor suspicious traffic without affecting network performance, that is IDS. If it says stop threats in real time, that is IPS. The word prevent always points to IPS. Cloud service models appear on almost every Network Plus exam. You need to know what each gives you, what the customer manages, and what the provider manages. IaaS, Infrastructure as a Service, gives you virtual machines, storage, and networking. You manage the operating system and everything above it. The cloud provider manages the physical hardware. AWS EC2 is the classic IaaS example. PaaS, Platform as a Service, gives you a development environment. You manage your application and data. The provider manages everything else, including the operating system and runtime. Heroku is PaaS. SaaS, Software as a Service, gives you a finished application delivered over the browser. You manage nothing but the data you put into it. Microsoft 365 is SaaS. The shared responsibility model is a major exam topic. In IaaS, you are responsible for patching the operating system. In SaaS, the provider is responsible for everything except your data. In a scenario question, if a customer is asking who patches the operating system, the answer depends entirely on the service model. Cloud deployment models. A public cloud is owned by a third-party provider and resources are shared across many customers. A private cloud is dedicated to one organization and can be on-premises or hosted. A hybrid cloud combines public and private. A community cloud is shared among organizations with similar requirements, like multiple government agencies sharing infrastructure. Elasticity means the cloud automatically scales resources up and down based on real-time demand. High availability means the system remains operational even if a component fails, with minimal downtime. Fault tolerance means the system continues to operate with zero interruption, even if a component fails. High availability and fault tolerance are often confused on the exam. High availability minimizes downtime. Fault tolerance eliminates it. Multi-tenancy means multiple customers share the same physical infrastructure but are logically isolated from each other. Your data is separated, but the hardware underneath is shared. Ports and protocols are the most memorization-heavy section of Domain 1. The exam gives you a scenario and asks which port to open on a firewall or which protocol is responsible for a specific function. FTP, File Transfer Protocol, uses port 20 and port 21. In passive mode, FTP uses a random high port for data transfer instead of port 20. This distinction is a direct exam trap. SSH, Secure Shell, uses port 22. This is your secure remote access protocol, replacing Telnet. Telnet uses port 23. Telnet sends everything in plain text, including credentials. SSH replaced it for exactly that reason. SMTP, Simple Mail Transfer Protocol, uses port 25. This is the protocol for sending email between servers. DNS, Domain Name System, uses port 53 on both TCP and UDP. UDP handles standard queries because it is faster. TCP handles zone transfers between DNS servers and responses larger than 512 bytes. The exam expects you to know both. HTTP uses port 80. HTTPS uses port 443. If you see a scenario involving a web server that must encrypt traffic, port 443 is the answer. POP3, Post Office Protocol version 3, uses port 110. POP3 downloads email to the client device and typically removes it from the server. IMAP4, Internet Message Access Protocol version 4, uses port 143. IMAP4 synchronizes email across multiple devices and leaves the messages on the server. The exam scenario distinction: multiple devices accessing the same inbox means IMAP4. SNMP, Simple Network Management Protocol, uses port 161. This is the protocol for monitoring and managing network devices remotely. LDAP, Lightweight Directory Access Protocol, uses port 389. This is for querying directory services like Active Directory. LDAP-S, that's LDAP over SSL, uses port 636 for encrypted directory queries. SMB, Server Message Block, uses port 445. This is the protocol for Windows file and printer sharing. RDP, Remote Desktop Protocol, uses port 3389. This is for graphical remote access to Windows systems. The IP protocol numbers are also tested. TCP is protocol number 6. UDP is protocol number 17. ICMP, Internet Control Message Protocol, is protocol number 1. GRE, Generic Routing Encapsulation, is protocol number 47. ESP, Encapsulating Security Payload used in IPsec, is protocol number 50. DNS trap, one more time. The exam will ask why DNS uses both TCP and UDP. UDP is for everyday queries because speed matters. TCP is for zone transfers and large responses. If you see zone transfer in the question, the answer is TCP on port 53. Copper cable categories are directly testable with specific speeds and distances. Cat5e supports up to 1 gigabit per second over 100 meters. This is the minimum you would install in any modern deployment. Cat6 supports up to 10 gigabits per second over 55 meters or 1 gigabit over the full 100 meters. Cat6a extends 10 gigabits to the full 100-meter distance. Cat8 reaches 40 gigabits, but only over 30 meters, so it is used inside data centers between closely placed equipment. For fiber optic cable, multi-mode fiber uses LED light sources and is designed for shorter distances, typically within a single building or campus. Single-mode fiber uses laser light sources and is built for long distances, across campuses or between cities. If a question involves connecting two buildings across a city, the answer is single-mode fiber. Fiber connectors each have a specific form factor. LC connectors are small form factor, used in high-density patch panels and SFP modules. SC connectors are square with a push-pull mechanism. ST connectors use a bayonet twist lock and are common in older installations. MPO connectors support multiple fibers in a single connector and are used for high-density data center cabling. Transceivers connect fiber cables to network equipment. SFP modules, small form factor pluggable, support 1 gigabit. SFP Plus modules support 10 gigabits. QSFP, quad small form factor pluggable, supports 40 gigabits. QSFP Plus supports 100 gigabits. If the exam gives you a data rate and asks which transceiver to select, match the rate to this list. The 802.11 wireless standards are heavily tested. 802.11a operates at 5 GHz with a max speed of 54 megabits per second. 802.11b operates at 2.4 GHz with a max of 11 megabits per second. 802.11g operates at 2.4 GHz with a max of 54 megabits per second. 802.11n, also called Wi-Fi 4, operates at both 2.4 and 5 GHz with a max speed of 600 megabits per second. This was the first standard to introduce MIMO, which uses multiple antennas to transmit and receive simultaneously. 802.11ac, or Wi-Fi 5, operates only at 5 GHz, with speeds approaching 7 gigabits per second using MU-MIMO. 802.11ax or Wi-Fi 6 operates at both 2.4 and 5 GHz. Wi-Fi 6 extends this to the 6 GHz band. Wi-Fi 6 supports speeds approaching 10 gigabits per second and introduces OFDMA for improved efficiency in dense environments. Wireless trap. 2.4 GHz has longer range, but suffers from more interference because that frequency is shared with microwaves, baby monitors, and Bluetooth devices. 5 GHz has shorter range but far less interference and more available channels. If an exam scenario describes wireless interference in a dense office or apartment building, the answer is almost always to move to 5 GHz or configure the access point to use a non-overlapping channel. Topology questions present a scenario and ask which design or architecture fits the requirement. A star topology connects all devices to a central switch or hub. This is the dominant topology in modern local area networks. The advantage is that a failure in one device does not affect others. The weakness is that if the central switch fails, everything goes down. A bus topology connects all devices to a single shared cable. A failure anywhere on the cable takes down the entire network, rarely deployed in modern environments but still appears on the exam. A ring topology connects devices in a circle where data travels in one direction. A break in the ring disrupts the entire loop. Dual ring designs mitigate this by providing a backup path in the opposite direction. Mesh topology provides multiple paths between devices. A full mesh connects every device directly to every other device, providing maximum redundancy. A partial mesh connects only selected devices with multiple paths to reduce cost. Full mesh is expensive and is used in WAN connections between data centers where uptime is non-negotiable. The three-tier architecture is the standard for enterprise campus networks. The core layer is the high-speed backbone, handling traffic between distribution blocks and connecting to the internet or data center. The distribution layer handles routing, policy enforcement, and aggregates access layer switches. The access layer is where end devices, computers, phones, and printers connect to the network. Spine and leaf is the modern data center topology, replacing three-tier in dense compute environments. Every leaf switch connects directly to every spine switch. There are no direct leaf-to-leaf connections. This architecture provides predictable, low-latency paths and easy horizontal scaling because adding a new leaf switch gives it automatic connectivity to every spine. Topology trap. If a question says easy to add new devices and a failure in one device does not disrupt others, the answer is star topology, not mesh.
Mesh is about redundant paths between network segments. Star is about individual device connectivity in an office. IP version 4 addressing is the highest stakes section in Domain 1. Subnetting questions can eat significant time if you are not confident. You need to be fast. The three private IP address ranges defined in RFC 1918 are 10.0.0.0 through 10.255.255.255, which is a /8, 172.16.0.0 through 172.31.255.255, which is a /12, and 192.168.0.0 through 192.168.255.255, which is a /16. These addresses are not routable on the public internet. A PIPA, automatic private IP addressing, uses the range 169.254.0.0 through 169.254.255.255. When a device cannot reach a DHCP server during boot, it automatically assigns itself an PIPA address.
If you see a 169.254 address in an exam scenario, the immediate diagnosis is that the device cannot reach its DHCP server. The loopback address is 127.0.0.1. Any traffic sent to this address never leaves the device. It is used for testing the local TCP and IP stack. For subnetting, here is the CIDR reference chart you need memorized. /24 mask 255.255.255.0 254 usable hosts. /25 mask 255.255.255.128 126 usable hosts. /26 mask 255.255.255.192 62 usable hosts. /27 mask 255.255.255.224 30 usable hosts. /28 mask 255.255.255.140 14 usable hosts. /29 mask 255.255.255.248 6 usable hosts. /30 mask 255.255.255.252 2 usable hosts. This is the smallest subnet used for point-to-point links between two routers. /32, a host route representing a single IP address. The usable hosts formula is 2 to the power of the number of host bits minus 2. You subtract 2 because the network address and the broadcast address cannot be assigned to any device. The subnetting shortcut for the last octet is subtract the last octet of the subnet mask from 256 to get the block size. For a /26, the last octet of the mask is 192. 256 minus 192 equals 64. Your subnets start at .0, .64, .128.192. Any address that falls inside one of those blocks belongs to that subnet.
The classful ranges. Class A spans 1.0.0.0 to 126.255.255.255. Class B spans 128.0.0.0 to 191.255.255.255. Class C spans 192.0.0.0 to 223.255.255.255. Class D, from 224 to 239, is reserved for multicast. Class E is reserved for experimental use. Neither can be assigned to a host. This is an exam trap when they show you a 225.x address and ask if it is valid for a host. It is not. The final objective covers the modern concepts that the Network Plus exam expects you to understand at a conceptual level. You do not need to configure these. You need to know what they are and when they are used. SDN. That's software-defined networking, separates the control plane from the data plane. The control plane makes forwarding decisions. The data plane executes them and moves packets. In a traditional network, both planes run on the same hardware. In SDN, a centralized controller manages the control plane for all devices across the network. This makes the network programmable through software and eliminates the need to manually configure each device independently. SD-WAN, Software-Defined Wide Area Network, applies SDN concept to wide area network connections. It allows traffic to be routed intelligently across multiple links, such as MPLS and broadband, based on application type and policy rather than static routing. Critical applications get priority paths. Less critical traffic uses cheaper links. IAC,
Infrastructure as code means managing and provisioning network infrastructure using configuration files and automation tools instead of manually logging in to each device. Terraform is used for provisioning infrastructure. Ansible, Puppet, and Chef are used for configuration management and ensuring devices remain in a desired state. The exam expects you to recognize the category each tool belongs to. VXLAN, Virtual Extensible LAN, extends Layer 2 network segments over a Layer 3 IP fabric. Traditional VLANs are limited to 4,096 segments. VXLAN supports over 16 million logical network segments. This is critical in large cloud and multi-tenant data center environments, where thousands of customers share the same physical infrastructure but must remain completely isolated. Zero Trust is a security architecture built on the principle that no user, device, or network segment is inherently trusted, regardless of whether they are inside or outside the corporate network. Every access request is authenticated, authorized, and continuously validated. The core principle is never trust, always verify. SASE, Secure Access Service Edge, combines SD-WAN with security-delivered cloud services. Instead of routing all traffic back to a central data center for security inspection, the security functions are moved to the cloud edge, closer to where users are actually located. This reduces latency and eliminates the bottleneck of centralized inspection for distributed workforces. For IP version 6 migration, 3 strategies appear on the exam. Dual stack means running both IP version 4 and IP version 6 simultaneously on the same interface. The device can communicate using either protocol. Tunneling means encapsulating IP version 6 traffic inside IP version 4 packets to carry it across a network that does not yet support IP version 6 natively. NAT64 translates IP version 6 addresses to IP version 4 addresses, allowing devices that only speak IP version 6 to communicate with IP version 4 resources. That is Domain 1, all 23% of it covered in one session. If you can recite the OSI layers and map devices and protocols to each one, if you know your port numbers without hesitating, and if you can subnet a /28 without reaching for a calculator, and if you can explain the difference between SDN and SD-WAN in a single sentence, you are ready for this domain. Domain 2 has 4 sub-objectives, covering routing, switching, wireless, and the physical installation, the racks, the cabling, the power. We start with routing because routing is where the most points are lost on exam day. 2.1 is routing. Routing technology has 3 jobs: decide where a packet should go, choose the best path to get there, and update that path when the network changes. Every line of every routing protocol exists to do one of those 3 things. When a router gets a packet, it looks at the destination IP address and walks its routing table. The lookup is not first match. The lookup is longest prefix match. If the table has a route for 10.0.0.0/8 and another route for 10.50.0.0/16, and the packet is heading for 10.50.4.200, the /16 wins. More specific always beats less specific. Memorize that order, because the exam will give you 2 routes to the same network and ask which one the router uses. The answer is the one with the longer prefix, regardless of which protocol learned it. Now, if 2 routes have the same prefix length, the router has to break the tie. That's what administrative distance does. Administrative distance is the credit rating of routing protocols. Static gets a 1, the highest credit. eBGP, External Border Gateway Protocol, gets 20. OSPF, Open Shortest Path First, gets 110. RIP gets 120. IBGP, Internal BGP, gets 200. The lower the number, the more the router trusts the source. So, if a static and an OSPF route both point to the same destination with the same prefix length, the router picks the static one every time. The mnemonic, always pick static. If the prefix length is the same and the administrative distance is the same, the router uses metric. Metric is the protocol's own measurement of cost. OSPF uses cost based on bandwidth. EIGRP, Enhanced Interior Gateway Routing Protocol, uses a composite of bandwidth, delay, load, and reliability. RIP uses hop count and caps out at 15 hops. The exam will rarely ask about metric in isolation. It will ask about the full decision order, longest prefix, then administrative distance, then metric. Burn that order in. Static routing versus dynamic routing comes up in scenario questions. Static is the printed map taped to your dashboard. You configure each route by hand, and it never changes unless you change it. Dynamic is ways. The router learns routes from its neighbors using a protocol, and when something goes down, the protocol reroutes automatically. Static wins on small networks, on stub networks with a single exit, and on links where you want zero protocol overhead. Dynamic wins on anything that has more than 3 routers or that needs to survive a link failure without a phone call. The 3 dynamic protocols the exam tests are BGP, OSPF, and EIGRP. BGP is the routing protocol of the Internet. It runs between autonomous systems, between separate organizations, and it uses path vector logic with policy attributes. OSPF is the open standard interior gateway protocol. It runs inside a single organization, uses link state, and converges fast. EIGRP is Cisco's hybrid. It uses distance vector with link state behaviors and is the fastest converging of the 3. If the exam describes routing between 2 ISPs, that's BGP. If the exam describes a multi-vendor campus needing fast convergence, that's OSPF. If the exam describes a Cisco-only network, EIGRP is an option, but OSPF is still a safe answer. Network Address Translation, NAT, lets multiple internal devices share a smaller pool of public addresses. Think of NAT as an office building reception. All 500 internal employees show up to the outside world as one address, the reception desk. PAT, Port Address Translation, is the same reception desk forwarding calls back inside the building using a specific extension number. PAT is what most home and small office routers actually do. The exam may use the term overloading, which is just PAT under a different name. NAT 1-to-1 means each internal address gets its own dedicated public address. NAT 1-to-many is overloading and uses port numbers to track the conversations. First Hop Redundancy Protocol, FHRP, lets 2 routers share one virtual gateway address so the network stays alive when one router dies. HSRP is Cisco's version. VRRP is the open standard. The hosts on the network think they're sending packets to one gateway, but 2 physical routers are silently behind it, with one active and one standby. If the active router dies, the standby takes over within seconds. The host never knows anything changed. A virtual IP, VIP, is the address shared by the FHRP routers. It's also the term used for the address presented by a load balancer in front of a server farm. Same idea, a single address that hides a redundant pool behind it. Sub-interfaces are how a router runs multiple VLAN gateways on a single physical interface. Each sub-interface gets its own VLAN tag and its own IP address. This is also called router on a stick. One physical cable, multiple logical gateways. If the exam describes a router with a single Ethernet link to a switch trunk port and asks how multiple VLANs route through it, the answer is sub-interfaces. That wraps 2.1. Routing is the heaviest section in Domain 2 because the exam loves to test the decision order. Longest prefix wins first, administrative distance breaks ties second, Metric breaks ties third. If you remember nothing else from this section, remember those three in that order.
2.2 is switching. Switches operate at layer 2 and forward frames based on MAC addresses. But the exam does not test you on what a switch does. It tests you on VLANs, trunking, spanning tree, and the interface settings that quietly break a network when they are wrong. A VLAN is a logical separation of traffic on the same physical switch. Think of VLANs as apartments in the same building. Same physical hardware, completely separate living rooms. Traffic in VLAN 10 cannot reach traffic in VLAN 20 unless you build a hallway between them, and that hallway is a router or a layer 3 switch. The VLAN database is the configuration list stored on the switch that tracks which VLANs exist and what their numbers are. An SVI, Switched Virtual Interface, is the Layer 3 interface that gives a VLAN its gateway address on a Layer 3 switch. Trunk ports carry traffic for multiple VLANs over a single link. Access ports carry traffic for one VLAN only. A trunk port is a multi-lane highway with traffic for every district sharing the road. An access port is a single-lane neighborhood street going to one house. The exam will give you a misconfiguration where a port is set to access mode, but the user expects multiple VLANs, and the symptom is some traffic working and other traffic dropping. That is an access port that should be a trunk. 802.1q is the trunk tagging standard. When a frame leaves a switch on a trunk port, the switch inserts a 4-byte tag inside the Ethernet frame between the source MAC and the Ether type. That tag tells the next switch which VLAN the frame belongs to. The tag is removed when the frame exits a trunk on its way to an access port. The mental model is TSA luggage tags on a multi-airline flight. Each piece of luggage gets a tag at check-in. The gate agents at the next airport read the tag to know which carousel, and the tag comes off when the bag goes home. The native VLAN is the one VLAN whose traffic crosses the trunk untagged. By default, it is VLAN 1. This is a security trap. If both sides of the trunk do not agree on the native VLAN number, traffic gets dropped, or worse, it leaks into the wrong VLAN. Match the native VLAN on both sides of every trunk, and change it from 1. Never leave native VLAN at the default. Voice VLAN is a special VLAN for IP phones. The switch port carries normal data on the access VLAN and tagged voice traffic on the voice VLAN over the same single port. The phone gets its own VLAN for quality of service treatment, and the computer plugged into the back of the phone gets the regular VLAN. One cable, 2 VLANs, 2 different priorities. Link aggregation, LACP, combines multiple physical links into a single logical link. 4 1 gigabit cables become one 4 gigabit logical link. It also provides redundancy. If one of the 4 cables fails, the other 3 keep the link alive. LACP is the standard for negotiating the bundle. If you see the exam describe combining cables for both speed and resilience, the answer is link aggregation. Speed and duplex settings cause more outages than any other Layer 2 issue. Modern switches auto-negotiate both, but auto-negotiation requires both ends to be set to auto. If one end is hard-coded to 100 megabits full duplex and the other end is set to auto, the auto end will detect 100 megabits but fall back to half duplex. That is a duplex mismatch. The symptom is a slow connection with late collisions and lots of cyclic redundancy check errors. The fix is either both ends auto or both ends hard-coded to match.
Spanning Tree Protocol, STP, prevents loops on Layer 2 networks. Without STP, if you connect two switches with two cables, a broadcast frame will circle between them forever, multiply, and bring the network down in seconds. STP is the traffic cop at a roundabout with too many entrances. It blocks one path per destination, so cars actually leave the roundabout instead of looping forever. The cost is a small delay every time the topology changes. STP has 5 port states. Disabled is the off state. The other 4 happen in order: blocking, listening, learning, forwarding. The memory hook is Brock listens, learns, forwards. Blocking is the port refusing to forward traffic because STP decided this path would cause a loop. Listening is the port watching for BPDUs, bridge protocol data units, to figure out the network's topology. Learning is the port building its MAC address table. Forwarding is the port working normally. The root bridge is the one switch STP elects to anchor the spanning tree. Root election is based on bridge ID, which is a combination of priority and MAC address. Lower bridge ID wins. The default priority is 32,768, so in practice, the switch with the oldest MAC address becomes root unless you manually set priority lower on the switch you want to be root. Original STP, defined in 802.D, takes 30 to 50 seconds to converge after a topology change. That's too slow for modern networks. RSTP, Rapid Spanning Tree Protocol, defined in 802.W, converges in under 6 seconds and is what runs on almost every modern switch by default. MSTP, Multiple Spanning Tree Protocol, lets multiple VLANs share a single spanning tree instance, which scales better in large networks. The exam wants you to know STP is slow, RSTP is fast, and MSTP scales. MTU is the maximum transmission unit. The largest frame size and interface will forward without fragmenting. The default Ethernet MTU is 1500 bytes. Jumbo frames are frames larger than 1500 bytes. They're used in storage networks and high-throughput data center environments because they reduce the per-frame processing overhead. The exam trap: MTU must match on both ends of a link. If one end is set to jumbo and the other is set to 1500, the link will silently drop the oversized frames. Match MTU everywhere on a path that uses it. That wraps 2.2. The VLAN and trunking section is where most exam points hide. If you can explain native VLAN, the duplex mismatch symptom, and the order of the 4 STP forwarding states, you're in good shape. 2.3 is wireless. Wireless is short because the exam tests less depth here than on routing or switching, but the trap density is high. A wireless channel is a slice of frequency that an access point and its clients use to talk. Channel width is how wide that slice is. Wider channels carry more data, but cause more interference. 20 MHz is the standard width. 40, 80, and 160 are wider channels used in 802.11n, AC, and AX, respectively. The trade-off is real. A 160 MHz channel sounds great on a spec sheet, but in a dense office, it picks up every other wireless network in range. Non-overlapping channels in the 2.4 GHz band are 1, 6, and 11. Those are the only 3. Any other channel in 2.4 overlaps with at least one of those. If you have 3 access points in a building, you assign them channels 1, 6, and 11 so they do not step on each other. Use channel 4 and you are interfering with both 1 and 6. Regulatory impacts vary by country. The US FCC, the European ETSI, and the Japanese telecom regulator all allow different channels at different power levels. 802.11h is the standard that lets access points coordinate with radar and weather systems on the 5 GHz band. If you deploy an access point in a country and find certain channels are unavailable, that is regulatory restriction, not a fault. The 3 frequency bands are 2.4 GHz, 5 GHz, and 6 GHz. 2.4 is the crowded apartment building. Every neighbor's microwave, baby monitor, and Bluetooth is on the same channels. 5 GHz is the suburb. More channels, less interference, shorter range. 6 GHz is the gated community. It was opened by the FCC in 2020 for Wi-Fi 6E, gives you 14 non-overlapping 80 MHz channels, and almost nothing else is on it yet. Band steering is the feature on dual-band and tri-band access points that nudges capable clients onto the higher frequency to relieve congestion on 2.4. SSID is the wireless network name, the storefront sign on a coffee shop. BSSID is the MAC address of a single access point's radio. ESSID is the same logical network across multiple access points, all advertising the same SSID so clients can roam. Network types on the exam are infrastructure, mesh, ad hoc, and point-to-point. Infrastructure is the standard model where clients connect to access points and the access points connect to a wired backbone. Mesh has the access points themselves talking wirelessly to each other to extend coverage without running cables to every spot. Ad hoc is a temporary peer-to-peer link between 2 clients, no access point. Point-to-point is a long-distance wireless link between 2 specific locations, often using directional antennas across miles. Encryption. WPA2 has been the standard since 2004 and uses AES. WPA3 is the current standard, mandatory for new Wi-Fi 6 and 6E certification, and uses simultaneous authentication of equals, which protects against offline password guessing. If the exam asks for current best practice, the answer is WPA3. Guest networks are isolated SSIDs that give visitors internet access without exposing the internal network. Captive portals are the splash pages that pop up before granting access. You've seen them in hotels and airports. They handle authentication, terms of service, and sometimes payment. The authentication question on the exam is PSK versus enterprise. PSK, pre-shared key, is the password you share with everyone connecting to the network. Easy to deploy, hard to revoke when someone leaves. Enterprise mode uses 802.1x, which authenticates each user individually against a radius server. Every user gets their own credentials. If a user leaves the company, you disable their account once and they lose all access. PSK for home and guest, enterprise for corporate. Antennas come in 2 main types. Omnidirectional antennas radiate in all horizontal directions like a light bulb. They're used in standard office access points to cover a circular area. Directional antennas focus the signal in one direction, like a flashlight. They're used for point-to-point links between buildings or to cover a narrow area like a hallway. Access point modes are autonomous and lightweight. Autonomous access points run independently, with full configuration on each one. Lightweight access points are dumb radios controlled by a central wireless LAN controller, a WLC. The controller handles configuration, security, roaming, and channel management for all the access points. Lightweight wins in any enterprise deployment because you configure once, not 50 times. That wraps 2.3. The 4 wireless points to nail are non-overlapping channels are 1, 6, and 11. WPA3 is current best practice. Enterprise authentication uses 802.1x with a radius server, and lightweight access points are managed by a WLC. 2.4 is the physical installation, racks, cabling, power, environmental. This is the most visual sub-objective. The exam tests it with scenario questions about what to deploy where. The intermediate distribution frame, IDF, and the main distribution frame, MDF, are the two cable termination points in a building. The MDF is the central wiring closet where the building's network gear lives, including the connection to the outside world. The IDF is the satellite wiring closet that aggregates cable runs from one section of the building back to the MDF. A multi-story office building typically has one MDF in the basement and one IDF per floor. Racks are sized in U units. 1 U equals 1 3/4 inches of vertical space. A standard rack is 42 U tall. Equipment is labeled with its U height, so you can plan rack layout. A 1 U switch takes 1 slot. A 2 U server takes 2 slots. The half-depth and full-depth dimensions matter because some racks have limited rear clearance. Port-side exhaust and port-side intake describe the airflow direction of network gear. In a data center hot aisle, cold aisle layout, all the cold air enters from the front of the racks. All the hot air exits from the back of the racks. Switches and routers must match this airflow inside the rack, so they pull cold air from the cold aisle and exhaust hot air into the hot aisle. Port-side intake means the air pulls in from the side with the cable ports, which is the data center cold aisle. Port-side exhaust is the reverse. Mismatching airflow inside a single rack causes the switch to overheat by pulling its own exhaust back in. Patch panels are the structured cabling termination points at each end of a run. Every cable from the wall jack lands on a patch panel in the wiring closet, where a short patch cable connects it to a switch port. The benefit is you change patch cables, not infrastructure cables. The wall-to-panel cable gets installed once and stays for the life of the building. Fiber distribution panels do the same job for fiber. They aggregate fiber strands from outside plant runs into a central termination point with LC or SC connectors. Lockable cabling is exactly what it sounds like. Locking patch cables or locking ports on the gear prevents someone from accidentally or deliberately unplugging a connection. Used in data centers and in environments with high security or compliance requirements. Power for the rack comes from two sources. UPS, uninterruptible power supply, is the battery backup that keeps gear alive through short power dips and gives the network administrator time to shut down gracefully during a longer outage. PDU, Power Distribution Unit, is the rack-mounted power strip that distributes power from the UPS or wall circuit to all the gear in the rack. The exam may give you a scenario where a server stays up but loses connectivity during a power blip. That is a network device on the wall circuit, not the UPS. Move the network gear behind the UPS. Power load is the total wattage of all the gear in a rack. It must not exceed the circuit's rating. Voltage matters because most enterprise gear is dual voltage, supporting both 110 and 220. Dense data centers run on 220 because higher voltage means less current for the same wattage, less heat, and lower copper costs. Environmental controls, humidity, temperature, and fire suppression. Humidity below 30% risks static electricity discharge that can damage components. Humidity above 60% risks condensation and corrosion. Target humidity in a network closet or data center is 40 to 60%. Target temperature is 64 to 81 degrees Fahrenheit at the rack inlet. Hotter than that, and gear starts to fail. Fire suppression in modern data centers is clean agent, like FM200 or Energen, because water sprinklers will destroy electronic equipment. Clean agents displace oxygen or absorb heat without damaging the gear. That wraps 2.4. The high-frequency exam points, IDF connects back to MDF, match airflow direction inside the rack. Patch panels separate infrastructure cabling from patch cabling, UPS protects against power dips, and clean agent suppression protects against fire without destroying the gear. That is Domain 2, all 20% of it. You're ready for this domain if you can recite the routing decision order without hesitating, longest prefix, then administrative distance, then metric. If you can explain in one sentence why a duplex mismatch causes late collisions. If you can name the 4 STP forwarding states in order. If you can recall that non-overlapping channels in 2.4 GHz are 1, 6, and 11, and if you can explain why an IDF connects to an MDF and not the other way around. Most students who fail the Network Plus do not fail because the material is hard. They fail because they treated routing protocols and spanning tree as concepts to read about, not patterns to recognize on the exam day. The Network Plus retake costs $390. That's the real price of passive study. Head to TechVaultAcademy.com and take the free Network Plus Readiness Assessment. 3 minutes, no credit card. It tells you exactly which subobjectives in this domain still need work, so you walk into the test center knowing exactly what you have and what you don't. While you're there, grab the free N10-009 study roadmap. It maps every subobjective to the time you have left before your exam date, so you spend that time on the right material. Domain 3 ships next. This is the domain that fails people who walked in feeling ready, not because it is hard, because it is a memorization minefield. DNS record types that all look almost identical. SNMP versions that differ by exactly one feature. RPO and RTO, 2 acronyms every candidate swaps the moment the clock starts ticking. This is Domain 3, Network Operations. 19% of the exam, and almost all of it comes down to whether you drilled the details or just read them. Domain 3 has 5 subobjectives covering documentation and change control, network monitoring, disaster recovery, the network services that keep addressing and names and time working, and the ways you reach a device to manage it. We start with documentation because documentation is the connective tissue every other network task leans on. 3.1 is documentation and change management. The exam tests whether you know which document does which job, and it tests the formal processes that keep a network from drifting into chaos. Start with diagrams. A physical network diagram shows the actual layout, every device, every interface, every cable, where each wire physically runs. It's the electrician's blueprint. A logical network diagram ignores the wiring and shows how the network connects at a higher level. It's the subway map. It doesn't care which street you're on, only which stations connect to which ones. You use the logical diagram to plan a new site and the physical diagram to find a bad cable. The exam also layers diagrams by OSI level. Layer 1 is the physical cabling, Layer 2 adds MAC addresses, and Layer 3 adds IP addresses. Same network, 3 levels of detail. A rack diagram is a head-on view of the equipment rack, like a seating chart for the data center. It lets you tell a remote technician to pull the device in row 3, rack W, unit 15, and they put a hand on the exact box without ever badging in. A cable map, or wiring diagram, shows where every cable run terminates, and it usually lives on the wall of the wiring closet in the IDF or the MDF. Each desk drop is numbered, so a jack on the floor maps to a port on the patch panel. Then there's asset tracking. Every laptop, switch, router, and firewall gets a tag, often a barcode or an RFID tag, and lands in an asset database. That database drives trouble tickets, financial depreciation, warranty tracking, and software license counts. IP address management, called IPAM, is the same idea but for addresses. It's the hotel front desk's room ledger. Which device holds which address, since when, and which addresses are still free. IPAM covers both IPv4 and IPv6 and flags when a scope is about to run dry. A service level agreement, an SLA, is a contract that defines the minimum service a provider will deliver, 99.99% uptime, no more than 4 hours of unscheduled downtime. It's a written promise with penalties attached. And for wireless, a site survey maps every access point and frequency in range, and a heat map shows how the signal propagates as you walk the building. Now the processes. Configuration management is about consistency. The production configuration is the standard build rolled out to every device of a type. The golden configuration, also called the baseline, is the master recipe that certifies a system is set up correctly. An integrity check compares a running device against that baseline. If they differ, you either fix the device to match the baseline, or you accept the change and update the baseline to a new version. Before you change anything in production, you back up the current config, or for a virtual machine, you take a snapshot. That's your save point. If the change breaks something, you reload. Lifecycle management is where the exam plants a clean trap. End of life, EOL, means the manufacturer stops actively developing a product. It may still ship security patches, but no new features. End of support, EOS, means the manufacturer stops everything, including security updates. That's the dangerous one. A device past end of support will never receive another security fix, so it becomes a standing liability on your network. If the exam asks which milestone is the real security concern, it's end of support, not end of life. Decommissioning is the other end of the cycle. When you retire a device, you sanitize or destroy its media first. You never toss a drive in the trash because the data outlives the hardware. And change management ties it together. It's a formal, documented process, a change window, an approval step, an install procedure, and a rollback plan all agreed before anyone touches a device. The pilot files the flight plan before takeoff. That wraps 3.1. If you remember one thing here, remember that end of support is the security cliff, because that's the day the patches stop forever.
3.2 is network monitoring. This subobjective is about how you watch a network that is too big to watch by hand, and the heavyweight here is SNMP. Start with the 2 ways to see traffic. Flow data, like NetFlow, gathers a summary of the conversations crossing your network, who talked to whom, on what port, how much data. It is metadata, the itemized phone bill, not the call itself. A packet capture, taken with a protocol analyzer, records the actual packets, every bit and byte, so you can read the conversation word for word. Flow data tells you the top 10 talkers on the network. Packet capture tells you exactly what one of them said. To get traffic to your analyzer, you use port mirroring, also called SPAN, Switched Port Analyzer. The switch sends a copy of the traffic from one port out to a monitoring port, while the original keeps flowing to its destination. It's a one-way mirror, copying the conversation to an observer who never touches the original. The alternative is a physical tap in the cable. Logs get centralized 2 ways. Syslog is the standard protocol for shipping log messages off a device, regardless of who made the device. Those logs flow into a SIM, a Security Information and Event Manager, which is the central security desk. It pulls every device's logs into one place, correlates them, raises alarms on anomalies like a burst of failed logins, and lets you go back in time for forensics, who authenticated when and what they touched. A few practices tie all of this together. You capture a performance baseline, a picture of a normal day, so you can recognize when today's traffic is abnormal. Availability monitoring is the simple up or down view, green for up and red for down, that fires an alert the moment a device drops. And network discovery, run on a schedule, walks the network to inventory every device on it, often using LLDP, the Link Layer Discovery Protocol, or its Cisco equivalent, CDP. Now, SNMP, the Simple Network Management Protocol. This is the management interface to your devices over one standard protocol.
A central station queries each device and stores the answers. The data on the device lives in a structure called the MIB, the Management Information Base, which is the directory of every value a device can report. Each value has an address called an OID, an object identifier. The MIB is the directory of questions. The OID is the exact question you ask. There are two ways the station and the device talk. Polling is the station asking on a schedule over port 161. The problem with polling is the gap between polls, where a fault can go unnoticed until the next one. That's why we have the trap. An SNMP trap is a message the device sends to the station on its own the moment something crosses a threshold over port 162. It's the smoke detector that calls you instead of you walking the hall sniffing for smoke. Polling is port 161. Traps are port 162. Know both numbers. Here's the part the exam tests hardest, the versions. Version 1 was the original, and it sends everything in the clear, no encryption. Version 2, specifically 2C, improved efficiency by letting you pull large bulk chunks of data at once, but it's still completely unencrypted. Anyone tapping the wire on version 1 or version 2C sees the entire conversation. Version 3 is the one that fixed it. Version 3 adds authentication and encryption. It uses a username and a password hash instead of the old method. The memory hook is simple. 1 and 2C talk in the clear, 3 is the vault. And the old method version 3 got rid of is the community string. A community string is just a password that grants access to the SNMP data, and the defaults are famously weak. Read-only is usually the word public, read-write is usually the word private. Community strings exist only in version 1 and 2C. That's the security weakness, and that's why version 3, which drops them for real authentication, is the answer whenever the exam asks for the secure choice. That wraps 3.2. The single highest value fact in this section is that SNMP version 3 is the only version that adds authentication and encryption. Everything below it is readable on the wire.
3.3 is disaster recovery. This is a short section with the highest acronym confusion rate in the entire domain, so we slow down and get the directions right. There are 4 metrics, and they are all measured in time. The two that matter most are RPO and RTO, and here is the one most people swap under pressure. Picture the moment the power dies. RPO, the recovery point objective, looks backward from that moment to your last good backup. It answers, how much data did I lose? If you back up every hour and you fail 59 minutes in, your RPO is up to an hour of data. RTO, the recovery time objective, looks forward from that same moment to the instant service is restored. It answers, how long until I am back up? The hook is point is the past, time is to recover. RPO is the recovery point behind you. RTO is the time ahead of you. Banks and hospitals demand an RPO near 0 because losing even minutes of data is unacceptable. An internal document server can tolerate a much longer RPO. The other two metrics describe hardware reliability. MTBF is mean time between failures, the average time a device runs before it breaks. A firewall might have an MTBF measured in years. MTTR is mean time to repair, the average time to fix it once it does break. The trick is the middle word. Between failures is how long it lasts. To repair is how long to fix it. MTBF high is good news. It means you need fewer spares. When disaster hits, you move operations to a recovery site, and there are 3 kinds. A cold site is an empty building, power and 4 walls, no equipment, no data. You truck in hardware and backups and people, and it is the cheapest and the slowest. A warm site sits in the middle. It has racks, power, maybe some hardware, but no live data. You show up, restore from backup, and run.
A hot site is a complete running replica of your data center, the same hardware, the same applications, and the data kept current through ongoing replication. You walk in and you're already live. The hook is temperature equals readiness. Cold is nothing ready, hot is everything running, warm is in between. Cold is cheapest, hot is most expensive, and you're paying for speed. High availability has two postures. Active-passive is one open register with a second cashier standing by, fully configured, copying the live state, doing nothing until the primary fails, then stepping in. That handoff is called failover. Active-active is both registers open, sharing the line. Harder to engineer because you have to track which flows go through which device. But when one dies, there's no failover to wait for because the survivor was already carrying traffic. It just absorbs the rest. Active-passive needs a failover. Active-active does not. And you test all of this. A tabletop exercise is the cheap test. Key people sit around a table and walk through the disaster on paper. Nobody moves the server. Everybody learns the steps. A validation test or full-scale test actually runs the recovery procedure against a real scenario, which is expensive but proves the plan works before you need it. That wraps 3.3. If you lock in only one thing, make it the direction of those two metrics. RPO looks back at lost data. RTO looks forward at restored time. 3.4 is the network services that keep addressing, names, and time working. This is the largest section in the domain because it carries DHCP, DNS, and the time protocols, and it's where the most exam points sit. Start with DHCP, the Dynamic Host Configuration Protocol, which hands out IP addresses automatically. The process is 4 steps, and the exam wants them in order. The mnemonic is DORA: discover, offer, request, acknowledge. Think of checking into a hotel. Discover, the client shouts, "Is anyone at the front desk?" Offer, a server answers, "Here is room 412. Request, the client says, "I'll take 412. Acknowledge, the server says, "Here is your key," and hands over the full configuration. Memorize the order, not just the letters. The client uses port 68, and the server uses port 67. And here's a structural trap. Every one of those 4 messages is a broadcast, and broadcasts do not cross routers. So if your DHCP server is on a different subnet from the client, the conversation never reaches it. The fix is a DHCP relay, also called an IP helper, configured on the router. The relay hears the broadcast, converts it to a unicast aimed straight at the DHCP server on the far subnet, and converts the reply back to a broadcast for the client. It's the neighbor who hears the shout, walks it across the street, and brings the answer back. A DHCP scope is the pool of addresses defined for a subnet, along with the subnet mask, the lease time, and options like the default gateway and the DNS servers. You can carve out exclusions, addresses inside the range the server must never hand out, and you can create a reservation, which binds a specific MAC address to a fixed IP. A reservation is a parking spot with the device's name painted on it. The printer gets the same address every time, managed centrally from the server instead of typed into the printer by hand. And the lease has 2 renewal timers. At 50% of the lease, the T1 timer fires, and the client tries to renew with the same server it got the address from. If that server is gone, it waits until 87.5% of the lease, the T2 timer, and then tries to renew with any DHCP server that will answer. T1 at half, T2 at 7/8. Now DNS, the domain name system, which translates names into IP addresses. DNS runs on port 53. It's the Internet's contacts app. You know the name, it hands you the number. At the top of the system sit the root servers, 13 clusters that point you toward the top-level domains, the .com, the .org, the country codes. Below them sit the servers authoritative for each individual domain. That word authoritative matters. An authoritative server holds the real original zone records for a domain. It's the birth certificate at City Hall. Those records live on a primary server where every change is made and copy automatically to one or more read-only secondary servers that also answer queries. A non-authoritative answer comes from a server that cached the information for speed. It's the photocopy in someone's drawer, usually fine, occasionally stale. How long a cached record lives is controlled by its TTL, its time to live, measured in seconds and set on the authoritative server. When the TTL expires, the cache is dropped and the next lookup goes back to the source. This is why a DNS change is not instant. Old cached copies linger until their TTL runs out. The way your computer actually resolves a name is a recursive query, and you should be able to describe it. Your device, the resolver, asks its local DNS server one question and waits. If the local server doesn't have the answer cached, it does all the legwork. It asks a root server, which points it to the .com server, which points it to the authoritative server for the domain, which finally returns the IP address. The local server hands that back to you and caches it for next time. You asked the concierge once, the concierge made all the phone calls and handed you a single answer. That's a recursive query, and the legwork stays hidden from you. There's one shortcut that happens before any of this. Every device has a local hosts file, a plain text file that maps names to addresses by hand, and the device checks it first. An entry in the hosts file overrides DNS entirely, which is why it's used to test a test server or to override a bad record while you troubleshoot. Now, the record types, because the exam will hand you 4 records that all look alike and ask which one a lookup returns. An A record maps a name to an IPv4 address. That's what a normal forward lookup returns. An AAAA record, 4 A's, sometimes called the quad A record, does the same job for IPv6. Count the A's. 1 A for the 4 numbers of IPv4, 4 A's for the long IPv6. A CNAME record, the canonical name, is an alias, a nickname that points one name at another name. A query for the alias returns the real name, and you may need a second lookup to get its address. An MX record, the mail exchanger, names the mail server for a domain, and it relies on an A record to resolve that server's actual address. A TXT record holds human-readable text, and it's where 2 important email records live: SPF, which lists the servers allowed to send mail for your domain, and DKIM, which carries the public key that verifies your signed email. An NS record names the authoritative name servers for the domain, and a PTR record, the pointer record, does the reverse lookup, mapping an IP back to a name. Here's the whole set as one line. A is one IPv4, quad A is the long IPv6, CNAME is a nickname, MX mails it, TXT talks, NS names the servers, and PTR points backward. DNS also has security extensions, and the exam separates 2 ideas that sound similar. DNSSEC digitally signs DNS records so you can verify they're genuine and were not tampered with, but signing is not encryption. With DNSSEC, the names still travel in the clear. To actually hide DNS traffic, you use DOT, DNS over TLS, which encrypts lookups on port 853, or DOH, DNS over HTTPS, which hides lookups inside normal encrypted web traffic on port 443. The hook is DNSSEC signs, DOT and DOH encrypt. Signing proves it's genuine, encryption hides it. Finally, time. NTP, the Network Time Protocol, synchronizes clocks across every device on port 123, and it matters more than it sounds. If 2 devices disagree on the time, their logs won't line up, and you can't correlate an incident. Worse, some authentication systems break on bad time. Kerberos, the authentication used on Windows networks, refuses to work if the client and server clocks are off by more than 5 minutes, which means wrong time can lock users out entirely. NTP, by default, runs in the clear, so NTS, Network's Time Security, adds authentication so you can trust the time source you're syncing to. And for environments that need extreme precision, like industrial systems, PTP, the Precision Time Protocol, synchronizes in hardware down to the nanosecond, far tighter than NTP's millisecond range. One more piece lives here: IPv6 self-addressing. Unlike IPv4, an IPv6 device can build its own address with no DHCP server at all, using SLAAC, Stateless Address Auto-Configuration. The device learns its subnet prefix by asking the local router, then generates its own interface portion, then uses duplicate address detection to confirm no one else already holds that address before it commits. It's a device walking into an empty theater, picking its own seat, and checking that nobody took it first. The protocol behind all this is NDP, Neighbor Discovery, which replaces IPv4's ARP and uses efficient multicast instead of broadcast. That wraps 3.4. The two highest value items are the DORA order, discover, offer, request, acknowledge, and the DNS record set, especially that an A record returns IPv4 and a quad A returns IPv6.
3.5 is network access and management, the ways you reach a device to run it and the secure way to do each one. This section is short and very testable. For a text console, you have two protocols that do the same job with opposite security. SSH, Secure Shell, on port 22 is encrypted. Telnet on port 23 does the same thing with no encryption at all. SSH is a sealed envelope. Telnet is a postcard anyone along the route can read. SSH was built to replace Telnet, so whenever the exam offers both, SSH is the answer. For a graphical session, RDP, the Remote Desktop Protocol, is Microsoft's tool for controlling a Windows machine, while VNC is the cross-platform alternative that runs on many operating systems. And to manage devices at scale, you use an API to push changes to hundreds of devices at once, instead of logging in to each one by hand. When the network itself is down, you fall back to a console connection, a physical serial cable plugged straight into a port labeled console, often through a USB to serial adapter. It works when you cannot ping the device because it does not depend on the network at all. That distinction is the heart of inbound versus out-of-bound management. Inbound management reaches the device over the existing production network by SSH or a web interface to its IP address. It's fixing the elevator by riding it. Out-of-bound management uses a separate path that does not touch the production network, a serial console or a modem on a phone line, so you can reach the device even when the network is completely down. It's the service stairwell that still works when the elevator is dead. If the exam describes recovering a device during a network outage, the answer is out of bound. To protect all of this, you funnel administrative access through a jump box, also called a jump host. It's one hardened, heavily monitored device that sits at the edge, and administrators connect to it first, then jump from it to the internal devices. One guarded lobby everyone must pass through. Because it's internet-facing and a target, you keep it patched and you require multi-factor authentication on it. And then there's the VPN, the Virtual Private Network, which takes traffic that would normally travel in the clear, encrypts it, and sends it across the public internet. It's a private armored tunnel dug through a public highway. The device that builds the tunnel is a VPN concentrator, and these days it's usually built into the firewall. There are two topologies. A site-to-site VPN permanently connects two locations, a bridge welded between two buildings, and the users at each site never know their traffic is being encrypted as it crosses. A client-to-site VPN, also called remote access, runs a software client on a single device, the laptop at a coffee shop tunneling back to headquarters. There's also a clientless option that runs inside a web browser using built-in browser encryption, so there's nothing to install. The last distinction is the one the exam loves: full tunnel versus split tunnel.
With a full tunnel, every bit of traffic from the device goes through the VPN to the concentrator, even your request to a public website, which then gets decrypted at headquarters, sent out to the internet, and routed all the way back. Everyone rides the company shuttle, even to the corner store. With a split tunnel, the client is smart about it. Corporate traffic goes through the encrypted tunnel, and ordinary internet traffic goes straight out to the internet directly. Shuttle for work, walk yourself to the corner store. A split tunnel is more efficient because it doesn't drag public traffic through headquarters, but that public traffic is not protected by the VPN. A full tunnel protects everything at the cost of efficiency. That trade-off is the answer the exam is testing. That wraps 3.5. The fact to carry out of this section is that out-of-bound management reaches a device when the network is down because it rides a path the network failure cannot touch. That's domain 3, all 19% of it. You're ready for this domain if you can name the difference between end of life and end of support without hesitating and say which one is the security cliff. If you can state that SNMP version 3 is the only version that adds authentication and encryption. If you can explain RPO and RTO in one sentence each with the right direction, one looking back at lost data and one looking forward at restored time. And if you can recite the DORA stages in order and say that an A record returns IPv4 while a quad A returns IPv6. And if you can explain when out-of-bound management saves you and what a split tunnel does that a full tunnel does not. Most people who fail the Network Plus don't fail because operations is hard. They fail because they read these distinctions once, felt like they knew them, and never forced themselves to say them out loud in the right direction under pressure. The N10-009 retake costs $390. That's the real price of passive study. Head to TechVaultAcademy.com and take the free Network Plus Readiness Assessment. 3 minutes, no credit card. It tells you exactly which sub-objectives in this domain still need work, so you walk into the test center knowing exactly what you have and what you don't. While you're there, grab the free N10-009 study roadmap. It maps every sub-objective to the time you have left before your exam date, so you spend that time on the right material. And if you want a place to ask questions as you study, our community is open. Domain 4 ships next. Domain 4 is where confident candidates get quietly humbled, not because security is deep, but because it is a pile of look-alike terms the exam loves to swap on you. Authentication and authorization, one letter apart and constantly confused. Radius and TACACS Plus, two protocols that do the same job under different rules. A rogue access point, an evil twin, and an on-path attacker. 3 things that blurred together at 11 at night the week before your exam. This is Domain 4, Network Security. It is 14% of the exam, the lightest weighted domain on the whole test, and that is exactly the trap. People skim it, and then they repay the $390 retake fee, not because security was hard, but because they read these definitions once, nodded, and never said the differences out loud. So that is what we're going to do here, the active version. Domain 4 has 3 sub-objectives: the core security concepts, the attacks you have to recognize on site, and the defenses that stop them. We start with the concepts because you cannot name an attack or pick a defense until you own the vocabulary the rest of the domain is built on. 4.1 is the security concepts. This is the widest sub-objective in the domain, the vocabulary chapter, and the exam mines it for definition traps. Start with the foundation every other security decision rests on, the CIA triad. 3 letters, 3 goals. Confidentiality means only the right people can read the data, and we get it through encryption and access control. Integrity means the data was not altered along the way, and we prove it with digital signatures. Availability means the data is actually there when you need it. Picture a vault. Confidentiality keeps strangers out. Integrity proves nobody swapped what's inside, and availability means you can still open it when you need to. confidential, intact, available. And note, this is the CIA triad of security, not the federal agency. Around that triad sit 4 terms the exam loves to line up and ask you to tell apart. A vulnerability is a weakness, an unlocked window in your system. A threat is the thing that could come through it, the burglar. An exploit is the burglar actually climbing through. And risk is the likelihood that it all happens, the odds the burglar finds your unlocked window in the first place. Vulnerability is the hole. Threat is the danger. Exploit is the action. Risk is the probability. Now, logical security, and it begins with encryption. Data exists in 2 states, and the exam wants you to protect both. Data in transit is data moving across the network, a letter traveling through the mail, and you protect it with encryption protocols like TLS, Transport Layer Security, and IPsec. Data at rest is data sitting on a drive, the letter locked in a filing cabinet, and you protect it with things like full disk encryption. The phrase to lock in is in transit versus at rest, the road versus the drawer, and both need encrypting. Encryption needs keys, and managing keys and certificates at scale is its own discipline called Public Key Infrastructure, PKI. Think of PKI as a passport system. One trusted authority, the certificate authority, issues and vouches for every identity. If the certificate authority signed a certificate, you can trust it because everyone already agreed to trust that authority, the way every border agent trusts a passport. A public trusted authority is what a web server uses so the entire internet trusts it. A self-signed certificate is one you issued yourself with no outside authority. It's an ID card you printed at home, perfectly fine inside your own organization where everyone already trusts you, but no stranger on the internet will accept it. Public authority for the public, self-signed for the inside. Now, the largest theme in this subobjective, Identity and Access Management, IAM, which is simply the discipline of controlling who gets to do what. Underneath it runs a framework you must know cold, the AAA framework, the 3 A's, authentication, authorization, and accounting. Authentication is proving you are who you say you are. Authorization is what you are allowed to do once you're in. Accounting is the record of what you did. Picture a nightclub. Authentication is the bouncer checking your ID at the door. Authorization is the wristband that says which rooms you can enter. Accounting is the guest log that records when you came and went. Prove it, permit it, log it. And here's the single most swapped pair in the whole domain, authentication versus authorization. They're 1 letter apart and the exam knows it. Authentication confirms who you are. Authorization decides what you may access. The hook? Authentication is who. Authorization is what. You authenticate first, then you're authorized. Never blur them into the word auth on exam day, because the question is testing exactly that distinction. When you authenticate once in the morning and then reach every system all day without logging in again, that is single sign-on, SSO. 1 wristband at the entrance gets you on every ride for the rest of the day. And because a single password can be stolen, we add factors. Multi-factor authentication, MFA, requires more than 1 type of proof, and the exam wants the categories. Something you know, like a password, something you have, like a phone or a hardware token, something you are, like a fingerprint, and somewhere you are, like a GPS location. A door that needs a key you carry and a code you know is far harder to beat than either one alone. One common something you have factor is a time-based one-time password, that rolling 6-digit code that changes every 30 seconds and is worthless the moment it expires. That is time-based authentication. Then there are the authentication protocols, and the exam tests 4 of them. Radius, the remote authentication dial-in user service, is the old universal protocol that nearly every device and operating system supports. It is what authenticates your wireless users through 802.1x against a central server. TACACS Plus, the Terminal Access Controller Access Control System, does the same general job but is strongly associated with Cisco. And here is the comparison the exam lives on. Radius encrypts only the password and leaves the rest of the packet readable. TACACS Plus encrypts the entire packet. Radius bundles authentication and authorization together. TACACS Plus separates all three A's. And Radius runs over UDP, while TACACS Plus runs over TCP. The memory hook ties three of those together. TACACS and TCP both start with T. Total packet encrypted, the three A's torn apart, and transmission control protocol. Radius rides UDP and only hides the password. Get that one anchor and you have answered the hardest 4.1 question on the test. Two more directory-style protocols. LDAP, the Lightweight Directory Access Protocol, is how you read and write a central directory of users and devices. It is the company phone directory. Look up a name and get the department, the location, the whole entry. If you log into Windows Active Directory, you are using LDAP underneath. And SAML, the open standard for authentication and authorization across different organizations, is a trusted hall pass. One identity provider vouches for you, hands you a signed token, and every other service honors that token without rechecking your password. That covers authentication. Authorization, the second A, is governed by two ideas. Least privilege means you give every user only the access their job requires and nothing more. You do not hand everyone the master key. And role-based access control, RBAC, assigns permissions by job role rather than by individual person. You define a shipping clerk role that opens the shipping doors, and whoever fills that role inherits exactly those rights. In Windows, you do this with groups. Roles get the keys, people get the roles. A few more concepts round out 4.1. Geofencing restricts access based on physical location, an invisible fence for your data. Step outside the building or the country and your access cuts off. Physical security shows up here too. Cameras, often called CCTV, give you the always watching eye that lets you rewind time after an incident. Locks protect the doors, from a physical key to an RFID badge to a biometric reader like a fingerprint. Then there are deception technologies, and the exam pairs two of them. A honeypot is a single decoy system, a fake safe stuffed with fake valuables and wired to record whoever tries to crack it. A honey net is a whole fake network of those decoys, an entire movie set building designed to keep an attacker busy while you study exactly how they operate. One is a honeypot, a network of them is a honey net. Compliance is next, and you need three names. PCI DSS, the Payment Card Industry Data Security Standard, is the card industry's own rulebook for anyone storing credit card data, and it requires segmentation of that data. GDPR, the European Union's privacy law that gives individuals control over their personal data, including the right to have it deleted. And data locality, also called data localization, is the rule that data collected in a country must physically stay inside that country. What is grown here stays here. The last piece of 4.1 is network segmentation, splitting the network so one compromised piece cannot reach the others, like firewalls between apartments. The exam names the segments it expects you to isolate. IoT, the Internet of Things, the smart sensors and doorbells and cameras that are convenient but rarely built with security in mind. The Industrial Internet of Things, IIoT, the machines on a manufacturing line talking to each other. SCADA, ICS, and OT, the supervisory control, industrial control, and operational technology that run power grids and factory floors and absolutely cannot be reachable from the office network. A guest network, the coffee shop Wi-Fi inside your building that reaches the internet but never your internal files. And BYOD, Bring Your Own Device, where you carve out a managed work area inside an employee's personal phone so the company can secure and wipe its part without ever touching their photos. That wraps 4.1. If you carry one thing out of this section, make it the Radius versus TACAX Plus split. TACAX Plus encrypts the whole packet, separates the 3 A's, and runs on TCP. Radius only hides the password and runs on UDP.
4.2 is the attacks. This is the densest cluster in the domain, the one the exam draws the most questions from. We will take each attack by what it actually does to you. Start with denial of service. A denial of service, a DOS, is any attack that makes a service unavailable, usually by overwhelming it with more traffic or requests than it can handle. It is jamming the only doorway so no real customer can get in. One attacker, one source. Now multiply that. A distributed denial of service, a DDoS, is the same attack launched from thousands of machines at once. Those machines are a botnet, an army of ordinary computers infected with malware and controlled remotely, all attacking on command while their owners never know. That is the whole difference the exam tests. One source is a DOS. A botnet of many sources is a DDoS. Attackers make it worse with amplification, where they send a tiny request to a public service like DNS or NTP and spoof the victim's address so the service fires a giant reply at the victim instead. It is shouting a small question into a canyon and aiming the echo at someone else. Several of the remaining attacks share one shape, so let me define it once. An on-path attack, the term that replaced man in the middle, is any attack where the attacker secretly sits between two parties, relaying their traffic while reading it and sometimes changing it. It is the dishonest translator who passes the conversation along but quietly edits it. Neither side knows the translator is there. Hold that picture because the next two attacks are how an attacker gets into that middle seat. The first is ARP poisoning. The Address Resolution Protocol, ARP, is how a device maps an IP address to a MAC address on the local network, and it has no authentication at all. It believes any answer it hears. So the attacker simply announces that the router's IP address belongs to the attacker's MAC address, and your machine believes it. From then on, every packet you send toward the router goes to the attacker first. It is relabeling the office mailboxes, so every letter for the boss lands on the spy's desk. That lands the attacker on path. The next is DNS poisoning, also called DNS spoofing. Here, the attacker corrupts name resolution, so a name points to the wrong IP address, swapping the entry in the phone book, so the bank's name now points to a thief's house. The attacker can poison the DNS server itself, poison the responses on the fly, or even edit the local hosts file on your machine, that plain text file the device checks before DNS and always wins. Poison any of those, and you type the right name and land on the attacker's server. Next, MAC flooding. Recall that a switch keeps a table mapping MAC addresses to its ports, sometimes called the CAM table, and that table has a fixed size. The attacker floods the switch with thousands of frames using fake source MAC addresses until that table overflows. When it's full, the switch fails open. It can no longer tell which port a destination lives on, so it falls back to flooding every frame out every port, behaving like a hub. Now the attacker sees everyone's traffic. Flood the table, fail open, and the switch forgets how to be a switch. Then VLAN hopping, getting from your own VLAN to one you should never reach, and the exam wants both methods. The first is switch spoofing. Switch ports can auto-negotiate a trunk, and a trunk carries every VLAN, so the attacker's machine pretends to be a switch, negotiates a trunk, and suddenly holds the all floors key. The fix is to never auto-negotiate trunks and configure them by hand. The second is double tagging. The attacker crafts a frame with two VLAN tags.
The first switch strips the outer tag and forwards the frame, and a second switch reads the inner tag and drops it onto a VLAN the attacker was never allowed on. It's a package with two shipping labels, where the first warehouse peels one off and the next sends it somewhere off limits. The defense is to change the native VLAN off the default and force tagging on it. Now, 3 rogue and twin attacks that blur together, so we'll pin them down. A rogue DHCP server is an unauthorized device handing out IP addresses, an imposter at the front desk, giving guests the wrong room keys, which breaks connectivity across the network. A rogue access point is an unauthorized wireless access point plugged into your wired network, usually by a careless employee who just wanted better Wi-Fi, an extra side door propped open. And an evil twin is the malicious version of that, a fake access point deliberately copying your network name, your SSID, and often turned up louder to overpower the real one so your devices connect to it. It's a counterfeit cell tower wearing your network's name, the cheat. Rogue is usually an accident. The evil twin is the rogue access point on purpose, and both can put the attacker on path. Then social engineering, attacking the human instead of the machine, and the exam names 4 techniques. Phishing is the forged email pretending to be a trusted sender to trick you into giving up credentials, a counterfeit letter on the bank's letterhead. Shoulder surfing is exactly what it sounds like, the stranger reading sensitive information off your screen over your shoulder. Tailgating is slipping through a secured door behind someone who legitimately badged in. And dumpster diving is mining the company trash for names, numbers, and printouts useful in a later attack. Email, eyes, door, and trash, 4 ways in that never touch your firewall. The last category is malware, malicious software, and you should be able to name the types on site. A virus needs you to run it to spread, so you carry it. A worm spreads on its own across the network with no human help, so it walks, which makes it the more dangerous of the two. Ransomware encrypts your files and demands payment for the key. A Trojan horse hides malware inside something that looks legitimate, a gift with a surprise inside. A rootkit hides itself down in the operating system where it's hard to find or remove, hiding in the floorboards. A keylogger records every keystroke, including your passwords, and ships them to the attacker. And you'll see adware and spyware that exist to show you ads or watch you, and a logic bomb that waits for a specific date or event and then detonates. The single best defense across almost all of them is the same. Keep your systems patched, because most malware rides in through a vulnerability you left unpatched. That wraps 4.2. The highest value distinction here is the simplest one. A denial of service comes from one source. A distributed denial of service comes from a botnet of many. And ARP poisoning and DNS poisoning are just 2 roads to the same on-path seat in the middle of your traffic. 4.3 is the defense. Now that you can name the attacks, this is the toolbox that stops them, and it falls into 4 buckets. Hardening the device, controlling who gets on the network, writing the traffic rules, and drawing the security zones. Start with device hardening, the basics that close the easy doors. Disable unused ports, both the physical switch ports nobody's plugged into and the open service ports on a host, because every open port is an entry point. It is locking the empty conference room jacks. And change default credentials the moment you install anything, because factory usernames and passwords are published online for every device model. Changing the lock the day you move in is the single highest return security action there is. Next, controlling who connects, which is Network Access Control, NAC. The headline technology is 802.1x, which forces a device to authenticate before it gets any network access at all, even when it is physically plugged in. It has 3 roles the exam names. The supplicant is the device trying to connect. The authenticator is the switch or access point it connects through, and the authentication server is the back-end RADI server that makes the actual decision. No badge, no network. Alongside it sits port security, a switch feature that ties a specific port to a specific MAC address and shuts the port down if a different device plugs in, gluing one device to one jack. And MAC filtering allows or denies devices by their MAC address, a hardware guest list. But know its weakness because a MAC address can be changed in software, so MAC filtering is security through obscurity. It slows an attacker down, it does not stop a determined one. One more hardening discipline is key management, keeping all your certificates and encryption keys in one controlled system so you know exactly when each one was issued, when it expires, and when to revoke it. A master key ring with an expiry calendar. Then the traffic rules, and the central one is the access control list, the ACL. An ACL is an ordered list of allow and deny rules, matched against traffic by source, destination, port, and more. Two things about how it runs are tested constantly. It is processed top to bottom, and the first rule that matches wins, so specific rules go above general ones. And at the very bottom sits an implicit deny. Anything that matches no rule is dropped automatically, even though no rule says so. The ACL is the bouncer's clipboard, read top down, first match wins, and if you're not on the list, you do not get in. Beyond the ACL are two finer filters. URL filtering allows or blocks traffic by web address or by category of site, a block list of street addresses your browser cannot visit. And content filtering inspects what is actually inside the traffic rather than just where it is going. An inspector reading the contents of the package, used to block malware, leaked documents, or unwanted material. URL filtering judges the destination, content filtering judges the payload. The last bucket is security zones, grouping the network so you can write one rule for a whole region instead of address by address. The core split is trusted versus untrusted, inside versus outside, your internal network versus the internet. And the zone you must know by name is the screened subnet, the old DMZ, a separate buffer zone for the servers you intentionally expose to the public, like a web or email server. It's the building lobby. Visitors reach the front desk and the public services, but the locked back office, your internal network, stays private. Public traffic lands in the screened subnet and never touches the inside. That wraps 4.3. The one to anchor is the ACL behavior. Top to bottom, first match wins, implicit deny at the end. If no rule allows the traffic is denied. That's domain 4, all 14% of it. You're ready for this domain if you can do 5 things without hesitating. If you can state the CIA triad and tell authentication from authorization in one breath, who you are versus what you may do. If you can give the radius versus TACAX plus split, whole packet versus password, 3 A's separated versus combined, TCP versus UDP. If you can hear an attack described and name it, one source DOS versus a botnet DDoS, ARP poisoning versus DNS poisoning, a rogue access point versus an evil twin, and if you can explain why MAC flooding turns a switch into a hub, and if you can recite how an ACL is read, top to bottom, first match, implicit deny. If you can do those 5 without hesitating, you own domain 4. If you stumbled on any of them, that's your tell. That's the exact pair to drill out loud until the difference is automatic. The Network Plus retake is $390, and that's the real price of reading these terms once and assuming they stuck.
Domain 5 is the one that exposes whether you actually understand networking or whether you only memorized it.
Because troubleshooting does not hand you a definition and ask you to repeat it. It hands you a broken network and a single symptom, and it asks for your next move. A cyclic redundancy check counter climbing on an interface, a switch port that quietly disabled itself overnight, a laptop stranded on a 169.254 address that cannot reach anything, a switch buckling under traffic that will not stop circling. This is Domain 5, Network Troubleshooting. 24% of the exam, the single heaviest weighted domain on the whole test, and it is almost all scenario questions, the kind that read like a help desk ticket. People study every fact in this domain and still repay the $390 retake fee, not because troubleshooting was hard, but because they never once practiced turning a symptom into a next step. So that is what we are going to do here, the active version. Domain 5 has 5 sub-objectives, covering the troubleshooting method itself, the cabling and physical problems, the routing and switching service problems, the performance and wireless problems, and the tools you use to find every one of them. We start with the method, because every other question in this domain is really asking the same thing. What is the next step? 5.1 is the troubleshooting methodology. This is the most important section in the entire domain because the exam tests this process more than any single technology, and it tests it the same way every time. It describes a situation, stops you in the middle of it, and asks what you should do next. If you know the steps in order, those questions are free. If you do not, you will guess, and you will guess wrong. Think of it the way a careful doctor works. Hear the symptoms, form a diagnosis, run a test to confirm it, plan the treatment, treat the patient, confirm they are actually well, and write it all down in the chart. Skip a step and you end up treating the wrong illness. There are 7 steps and they go in a fixed order. Here's the memory hook to lock them in. I even try pinging it very directly. Identify, establish a theory, test the theory, plan of action, implement, verify, document. Step 1 is identify the problem. This sounds obvious, but it is the step that determines everything after it. You gather information. You question the users, because the people experiencing the problem are your best source of what is actually happening. You identify the symptoms, and you accept that there may be more than one. A single ticket can hide several problems stacked on top of each other, and the exam wants you to approach multiple problems individually rather than assuming they are one. You ask the most powerful question in all of troubleshooting: what changed? Did someone move a cable in the wiring closet? Was a configuration edited yesterday? Was a device powered off? And where you can, you duplicate the problem. Because if you can reproduce it on demand, you can find its root cause. Think of the mechanic who needs to hear the engine make the noise before touching anything. If you cannot reproduce it, you're guessing. Step 2 is establish a theory of probable cause. Now that you know the symptoms, you form a hypothesis about what is causing them. And the first rule here is to question the obvious. Check that it's plugged in before you rebuild the engine, because the boring cause is the most common cause. When the obvious answer doesn't fit, you reach for one of 3 structured approaches. Top to bottom means you start at the top of the OSI model, at the application, and work your way down toward the cable. Bottom to top means you start at the physical layer, confirm the cable and the link, and work your way up toward the application. And divide and conquer means you cut the problem in half, test something in the middle of the stack, and eliminate half the possibilities in a single move. This is the step candidates love to skip. They jump straight from a symptom to a fix. The exam punishes that, because without a theory, you're just swapping parts and hoping. Step 3 is test the theory to determine the cause. This is the lab bench. You take your one suspect cause and you test it. If the theory is confirmed, you move forward. If it is not confirmed, you go back and establish a new theory, and you do not move on until a test actually supports what you believe. A theory you never tested is not a cause, it is a hunch. Step 4 is establish a plan of action to resolve the problem. Once you know the cause, you decide how you're going to fix it in the real production environment, not the lab. That plan includes timing, because many changes cannot happen during the business day and have to wait for a scheduled change control window. And a good plan always includes a rollback plan, a way to undo the change if it makes worse. Think of a surgeon's plan that always includes an exit strategy. Step 5 is implement the solution, or escalate. You execute the plan, and notice the words "or escalate" because the exam includes them on purpose. If the fix is above your authority or your skill level, the correct action is to hand it to someone who can resolve it. Escalating is not failing, it's part of the method. And in many organizations, the team that diagnoses the problem is not the team that implements the fix, so the change is handed from troubleshooting to operations, and that handoff is part of the process too. Step 6 is verify full system functionality and, where possible, implement preventative measures. This is the other step everyone skips. You don't stop when the symptom disappears. You confirm the entire system works, ideally with the same user who reported the problem. And then you put measures in place so it doesn't happen again. Don't just stop the bleeding. Make sure the patient can walk out the door. Step 7 is document findings, actions, and outcomes. You write down what was wrong, what you did, and what the result was, because the version of you a year from now should not have to start this investigation from zero. The documentation is the case file. That wraps 5.1. If you carry one thing out of this section, make it the order itself and the 2 steps people forget. Establish a theory before you touch anything and verify the whole system after you are done. When the exam asks what is the next step, the order is the answer. 5.2 is the cabling and physical interface issues. This is the bottom of the stack, and it is where a huge number of real problems actually live. When something will not connect at all, the cause is very often physical, so this is the layer a good technician checks early. Start with using a wrong cable type. With fiber, the 2 types are single mode and multi-mode, and they are not interchangeable. Single mode is a single beam of light fired straight down a very narrow core. Multi-mode is a wider core where the light takes multiple paths, bouncing its way to the other end, like a flashlight down a wide pipe. Plug a single-mode fiber where multi-mode belongs, or the reverse, and the light arrives garbled. You get signal errors and a link that struggles or will not come up. With copper, the equivalent mistake is using the wrong category. Categories 5, 6, 7, and 8 are built to carry progressively faster signals over set distances, like water pipes of increasing diameter. Use a category below what the standard requires, and you will see errors and a link that drops to a slower speed or fails. There's also the choice between UTP, unshielded twisted pair, and STP, shielded twisted pair. Shielded cable wears a metal raincoat that keeps electrical interference out, so it belongs in electrically noisy areas near motors, fluorescent lights, and power runs. Use unshielded cable in that environment, and the noise gets in. That noise has a name, and the exam tests several forms of signal degradation. Crosstalk is signal from one pair of wires bleeding into another pair, like your neighbor's phone conversation leaking faintly onto your line. Interference, often electromagnetic interference or EMI, is noise from an outside source getting into the cable. And attenuation is the natural loss of signal strength over distance, your voice fading as you walk farther from the person you're talking to. Every cable standard has a maximum distance precisely because of attenuation. 2 more physical faults round out the cable problems. Improper termination is a bad connector or a bad punchdown where the wires were not seated correctly into the jack or the plug. And transmit-receive transposed, where the transmit and receive pairs are wired to the wrong pins, is like crossing the hot and cold taps so nothing comes out the way you expect. Both show up the instant you test the cable, which is exactly why you test every cable you install. Now move from the cable to the interface, because interfaces keep counters that tell you when something physical is wrong. The first counter is the cyclic redundancy check error, the CRC error. Every Ethernet frame carries a checksum. If the frame arrives and the math no longer matches, the frame was corrupted in transit, and the CRC counter ticks up. A CRC count that keeps climbing is your earliest warning of a bad cable, a failing interface, or interference on the line. It's a sealed letter that arrived with the wax seal broken. Next are runts and giants, defined by size. The minimum legal Ethernet frame is 64 bytes. Anything smaller is a runt, a note too short to be real. The default maximum is 1518 bytes. Anything larger than the configured maximum is a giant, a parcel too big to fit through the mail slot. And then there are drops, frames discarded because a buffer was full when they arrived, like mail thrown away because the box was already stuffed. CRC means corrupt. Runts are too small. Giants are too big. Interfaces also report their state, and 3 states are tested together. Error disabled is a state the switch puts a port into all by itself, automatically, when it detects a problem like a port flapping up and down or a port security violation. It's a breaker that trips itself to protect the circuit. Admin down means a human being deliberately disabled the port with a command. That's a light switch a person flipped off on purpose. And suspended is a state a port enters the moment it comes up into a configuration that doesn't match the other side, classically a link aggregation mismatch, where one end runs the Link Aggregation Control Protocol, LACP, and the other end does not. Suspended is a new hire sent home because their paperwork doesn't match. Error disabled is the switch's choice, admin down is yours, and suspended is a mismatch. The last group in this subobjective is hardware. Power over Ethernet, PoE, delivers power and data over the same cable, and it fails in 2 tested ways. The first is exceeding the power budget. A PoE switch has a total wattage ceiling, like a power strip rated for only so many watts. Connect more powered devices than the budget allows, and the switch can't feed them all, so some will not power up. The second is a standard mismatch. The PoE standards are 802.3AF, the original, 802.3AT, which carries more power, and 802.3BT, which carries the most. A switch built only to the lower standard can't deliver the power a higher standard device demands. Next is transceiver mismatch. A transceiver is the modular optic you plug into a switch, and it has to match the fiber and the wavelength on both ends, marked in tiny numbers on the side. Grab the wrong one and you get signal loss, like screwing the wrong bulb into the socket. And finally, signal strength, measured in decibels per milliwatt, where every device has a receive sensitivity floor. If the light or signal arriving at the far end is weaker than that floor, the link can't read it, which is why you calculate a power budget for long fiber runs before you ever install them. That wraps 5.2. The one to anchor here is the interface counters. A climbing CRC count points at a physical problem, the cable or the interface, and runts and giants are simply frames that are too small or too big.
5.3 is the common issues with network services. This is where the network is physically fine, the cables are good, but traffic still does not get where it should because something in the switching or the routing logic is wrong. We will take switching first, then routing. On the switching side, the most dangerous problem is a switching loop. At the MAC address layer, there's no mechanism to count how many times a frame has been seen, so a frame caught in a physical loop between switches will circle forever, around and around, and as more traffic piles in, the switches are overwhelmed and the network grinds to a halt. That flood is called a broadcast storm. Here's the distinction the exam wants. The loop is the cause, the broadcast storm is the symptom, and the protection is spanning tree protocol, STP, the traffic cop that deliberately blocks one path so cars cannot drive around the block forever. No spanning tree, no break.
Spanning tree depends on electing a root bridge, the reference point the whole topology measures from. That election is won by the lowest bridge ID, and if two switches tie, the lowest MAC address wins. If the wrong switch is elected root, traffic takes inefficient paths, so root bridge selection is something you verify. Spanning tree then assigns every port a role and a state, forwarding or blocking, and holds ports in between while it decides, like a traffic light on every port. A port stuck blocking when you expected it to forward is a classic switching symptom. Two more switching issues. An incorrect VLAN assignment means a device gets a valid IP address but still cannot reach the device as it should because the switch port was placed in the wrong virtual LAN. You were handed a key to the wrong floor. You're in the building, on the wrong network, talking to no one. And an access control list misconfiguration, an ACL problem, is when the rules on a switch or router silently drop legitimate traffic. An ACL is read top to bottom, first match wins, and there's an implicit deny at the bottom, so anything not explicitly allowed is dropped. That means an empty or wrong ACL turns everyone away, like a bouncer's list where not being on the list means you do not get in. Now the routing side. A router forwards traffic by consulting its routing table, and several things go wrong there. Route selection can pick a path you didn't intend, and routing table issues, like a missing entry, mean the router simply has no road to the destination and drops the traffic. The fix for everything else is a default route, the gateway of last resort, written to the destination 0.0.0.0/0, which matches anything not matched by a more specific route. A missing or incorrect default route means traffic bound for the internet has nowhere to go. It's a GPS with no road to the destination. Then the addressing problems, and these are the most tested in the whole subobjective. Address pool exhaustion happens when a DHCP server runs out of available addresses. The symptom is a device that boots and assigns itself an automatic private IP address, APIPA, in the 169.254 range. That address only works on the local segment and routes nowhere. So remember this, 169.254 means DHCP never answered, whether the pool was exhausted or the server was unreachable. And the fix is to add addresses or shorten the lease time. Next, the classic Layer 3 trio, an incorrect default gateway, an incorrect IP address, or an incorrect subnet mask. Get this one distinction and you've answered the most common Layer 3 question on the whole test. A wrong gateway means local devices work fine, but nothing off the network does, because the gateway is the door out of your neighborhood, and that door is broken. A wrong subnet mask means you misjudge which devices are even local, so the machine tries to reach a true neighbor through the router or a remote host as if it were local, and some hosts simply fall off the map. Gateway breaks the way out, mask breaks who's a neighbor. And finally, a duplicate IP address, where two devices claim the same address, usually because one was statically configured onto an address already in a DHCP pool. It's two houses printed with the same street address, and the fix is to find the offender by pinging the address and checking which switch port its MAC shows up on. That wraps 5.3. The highest value anchor here is the gateway versus mask symptom split. Wrong gateway, the internet dies while local lives. Wrong mask, your own neighbors disappear. 5.4 is the common performance issues. This is the domain of the network is slow. And here is the secret every senior technician knows. If you have ever chased a slow network, the network itself is usually fine. Something on it is not. Your job is to find which something. Three related problems sit at the top. Congestion is simply more traffic than the link can carry, like rush hour with more cars than the road has lanes. When two 1 gigabit links both send full speed toward the same 1 gigabit destination, the excess piles into a buffer, and when the buffer fills, packets are discarded. Contention is multiple devices competing for the same resource at the instant, everyone trying to merge into one lane. And bottlenecking is a single choke point that limits everything behind it, the slowest checkout lane setting the speed of the whole store. The bottleneck might be a slow disk, a busy CPU in a router, or one overloaded link, so you drill into the path to find the narrowest point. That leads to a distinction the exam loves: bandwidth versus throughput. Bandwidth is the theoretical maximum a link can carry, the width of the pipe. Throughput is how much data actually moves through it in real conditions, the water that actually flows. They are never the same number. And over a path of several links, the slowest link sets the throughput for the entire route. Then, 3 measurements you must be able to separate instantly. Say these 3 out loud right now, because the exam will hand you a symptom and ask for the cause. Latency is delay, the time between the request and the response. Packet loss is data that never arrives at all, words dropping out of a phone call entirely. And jitter is the variation in delay, packets that should arrive at steady intervals, instead arriving bunched up and then late, like a drummer who cannot keep time. Jitter is the one that wrecks voice and live video, because those need a steady, predictable beat. Latency is slow, jitter is uneven, and loss is gone. The rest of this subobjective is wireless, where performance problems have their own shape. Interference is the biggest one, and on wireless, it usually comes from other access points sharing your frequencies. Channel overlap is the specific form the exam tests in the 2.4 GHz band, where only 3 channels, 1, 6, and 11, do not bleed into each other. Put an access point on any channel in between, and it overlaps 2 of them, dragging down everyone. Signal degradation is attenuation through walls and distance, and insufficient coverage is the dead zone where the signal simply runs out, both found by walking the space with an analyzer and building a heat map. 2 numbers describe how usable a wireless signal actually is. The Received Signal Strength Indicator, RSSI, measures how strong the signal is at the client, and the signal-to-noise ratio, the SNR, measures how far that signal rises above the background noise. A device decides when to roam from one access point to the next using thresholds on those 2 values. Client disassociation is a device repeatedly kicked off the network, sometimes from an attack against the older unprotected management frames, sometimes from a signal that fell below those thresholds. And roaming misconfiguration is when access points that share one network name are not configured identically, or the RSSI threshold is set so low that a device clings to a distant access point instead of handing off to the close one, the sticky client problem. That wraps 5.4. The anchor here is the 3-way split. Latency is slow, jitter is uneven, and loss is gone. And jitter is the one that ruins a voice call. 5.5 is the tools and protocols for troubleshooting. This is the densest cluster in the domain after the methodology, and the exam tests it by describing a symptom and asking which tool you reach for. So we will organize them by what they actually do. First, the command line tools, then the discovery and measurement protocols, then the hardware tools, and finally the commands you run on the device itself. Start with the command line. Ping is the first thing you run, an Internet Control Message Protocol, ICMP, echo, that asks a simple question: is this device reachable? It is knocking on the door to see if anyone is home. Traceroute, which on Windows is the command tracert, maps the full path to a destination, listing every router, every hop along the way. It does this with a clever trick, sending packets with a steadily increasing time to live, the TTL, so each router in turn reports back, dropping a breadcrumb at every hop. Use ping to learn whether a host is up or down, and use tracert to learn which hop along the path is the wall. One caution the exam likes here, because both tools lean on ICMP and many firewalls filter ICMP. A hop that shows only asterisks in the output is often not a dead router. It is a device that simply refuses to answer. There's a third tool that combines ping and trace, path ping on Windows and MTR on Unix systems, which walks every hop the way tracer does, but measures each one over time to reveal which hop is quietly losing packets. So remember the trio: ping for up or down, trace for which hop, and path ping for where it is losing. Next, name resolution. When you need to test the domain name system, the DNS, two tools ask it questions directly. NSLOOKUP is the older one, available everywhere, and DIG is the more detailed, preferred one. Both ask the phone book the same thing: what address belongs to this name? If a website fails by name but works by IP address, these are the tools that prove DNS is the problem. Now the tools that read your own machine. ipconfig on Windows and ifconfig, or the newer IP command on Unix systems, show your local configuration, your IP address, your subnet mask, your default gateway, and your DNS servers. It's pulling out your own ID card. And the most important detail for the exam, running ipconfig/all shows the full picture, and that's where you spot a missing default gateway or an address in the 169.254 APIPA range that tells you DHCP failed. Netstat, network statistics, shows the active connections to and from your machine and the ports your system is listening on, the call log of who you're talking to and which doors you're leaving open. The ARP command displays the Address Resolution Protocol cache, the local table that maps an IP address to a hardware MAC address, which is exactly how you hunt down a duplicate address. And the route command lets you view the routing table stored inside your own computer, the roadmap the machine uses to decide where to send traffic. Two more software tools close out the command line. TCPDump captures packets right at the command line, and a protocol analyzer, like the graphical tools, reads those captures back in a form a human can understand, a wiretap that records every word on the wire for later. And Nmap, the network mapper, scans a device or an entire address range to discover which hosts are alive, which ports are open, and what's running on them, like a building inspector knocking on every door to see which ones are unlocked. It's an active scan, sending real queries and studying the replies, so even a quiet device on the same subnet has a hard time hiding from it, which is exactly how you find rogue devices you didn't expect on the network. There are also two discovery protocols and a measurement tool worth naming. Link Layer Discovery Protocol, LLDP, and its Cisco equivalent, the Cisco Discovery Protocol, CDP, let network devices announce themselves to their neighbors so you can learn what is plugged into a switch port, its name, and its VLAN without logging into it, like devices wearing name tags. And a speed tester measures the actual throughput of a connection, the speedometer you run before and after a change, to prove it helped. Now the hardware tools, the physical instruments. A toner or tone generator with its inductive probe puts a tone on one end of a cable so you can find that cable's other end in a bundle of hundreds, a beeper you follow through the wall. A cable tester checks continuity, proving pin 1 connects to pin 1 and finding shorts or crossed wires. But here's the tool candidates reach for wrong every single time. A cable tester only proves the wire conducts. A cable certifier goes further and proves the cable actually meets a category specification, that it can carry the speed the standard promises. And a time domain reflectometer, a TDR, is sonar for a cable, sending a pulse whose echo tells you exactly how far down the break is. Continuity, category, crack. A tester proves continuity, a certifier proves category, a TDR finds the crack. A network tap is spliced into a link to copy traffic to an analyzer. A passive tap, common on fiber, needs no power, while an active tap is powered and regenerates the signal. A port mirror, or span port, does the same thing inside the switch by copying traffic to one port, but it shares the switch's own bandwidth, so for very high traffic links, a physical tap is the better choice. A Wi-Fi analyzer scans the wireless spectrum to show which channels are crowded, where the dead zones are, and where interference is coming from, drawn as a heat map. The most capable versions add a spectrum analyzer, which sees every signal on the frequency, not just Wi-Fi, so you can catch interference from a microwave oven or cordless phone that a Wi-Fi-only tool would never reveal. And a visual fault locator, a VFL, shines visible light down a fiber so that at a break or a sharp bend, the light leaks out and shows you exactly where the fault is, a flashlight for glass. Finally, the commands you run on the device itself, the show commands, where you ask the switch or router for its own records. Show MAC address table lists the MAC addresses the switch has learned and the port each lives on, which is how you find where a device is physically plugged in. Show route, or show IP route, displays the routing table so you can trace a path hop by hop. Show interface reports whether a port is up or down, its speed and duplex, and its error counters, the CRC errors and drops we covered earlier. Show config, or show running config, prints the active configuration so you can read exactly how the device is set up. Show ARP displays the device's own address resolution cache. Show VLAN lists the virtual LANs and which interfaces belong to each, the fast way to catch a port in the wrong VLAN. And Show Power reports the PoE budget and how much of it each port is drawing, so you know whether you can add another powered device. That wraps 5.5. The anchor here is matching the tool to the symptom. Ping to test reachability, tracert to find the failing hop, ipconfig/all to read your own configuration, and a certifier, not a tester, when you need to prove a cable meets its category. That's domain 5, all 24% of it. You're ready for this domain if you can do 5 things without hesitating. If you can recite the 7 troubleshooting steps in order and name the 2 that everyone skips, establish a theory before you act, and verify full system functionality after. If you can tell a cable tester from a cable certifier and read a CRC error, a runt, and a giant for what they are. If you can hear a layer 3 symptom and split a wrong default gateway from a wrong subnet mask, the outway versus who's a neighbor. If you can separate latency from jitter from packet loss in a single breath, slow versus uneven versus gone, and if you can hear a symptom and reach for the right tool, ping for up or down, tracert for which hop, and path ping for where it is losing. If you can do those 5 without hesitating, you own domain 5. If you stumbled on any of them, that's your tell, and that's exactly what to drill, out loud, until the next step comes without thinking. The Network Plus retake is $390, and that's the real price of passive study. Head to TechVaultAcademy.com and take the free Network Plus Readiness Assessment. 3 minutes, no credit card, and it tells you exactly which sub-objectives still need work, so you walk into the test center knowing precisely where you stand. While you're there, grab the free N10-009 study roadmap. It maps every sub-objective to the time you have left before your exam date, so you spend that time on the right material. And if you want a place to ask questions as you study, our community is open. The combined N10-009 review video is the one-shot replay of everything you just learned across 5 domains, start to finish, the night before your exam. Good luck. You're more prepared than you think.